Hello and good afternoon. My name is Ralf Greve from Hokkaido University's Institute of Low Temperature Science in Sapporo, Japan. I'm going to talk about reduced mass loss from the Greenland ice sheet under stratospheric aerosol injection and some general considerations about pros and cons of geoengineering techniques. Geoengineering techniques have been proposed to mitigate some of the worst impacts of global warming. They can be roughly categorized into three different groups, namely solar engineering, carbon dioxide removal, and targeted geoengineering. Here I'm going to look into solar engineering, in particular stratospheric aerosol injection. Stratospheric aerosol injection means that large amounts of aerosols, typically sulfate aerosols, are injected into the lower stratosphere. As indicated in the sketch here, they could be released by airplanes, for example, and the effect is then that part of the incoming solar radiation is reflected back to space and does not enter the troposphere, thereby counteracting to some extent the effect of global warming. I'm going to present the results of a recent study by John Moore, myself, and others, where we look into the impact of one particular SAI, stratospheric aerosol injection scenario called GeoMIP-G4 on the mass loss of the Greenland ice sheet. The background for this study was a visit of Professor Moore at my institute in December 2019 until February 2020. So it's already quite a while ago. For this study, we need climate forcings to drive the ice sheet models. Our model time is from the year 2015 until 2090, and we consider three different climate change scenarios, namely RCP 8.5, a worst case scenario, RCP 4.5, an intermediate scenario, and the already mentioned GeoMIP-G4, which is an RCP 4.5 with the additional assumption of 5 megatons per year SO2 injection into the lower equatorial stratosphere during the years 2020 until 2070. We use 4 different Earth system or climate models to derive the forcings for the ice sheet models for these 3 scenarios. They are listed here. I'm not going into details here. And as indicated here, so we use the results from these climate models for different scenarios as drivers for the ice sheet models. For the surface mass balance in particular, we require an intermediary model called SEMIC to derive this particular forcing. The second atmospheric forcing is the surface temperature, and on top of that, there's also an oceanic forcing, which consists of pre-computed retreat masks at the ice sheet margin as a consequence of warming ocean. These plots show the climate forcing for the 3 scenarios and the 4 different climate models. To the left, we see the surface mass balance anomaly. To the right, the surface temperature anomaly. So as for the surface mass balance, the 3 scenarios, RCP 8.5, 4.5, and G4, are indicated by the 3 colors. Red is 8.5, green is 4.5, and blue is G4. And same for the surface temperature. The thick lines in all cases are the ensemble means of the 4 Earth system models, while the thin lines show the individual results from the different Earth system models. So not very surprisingly, the impact in both cases, SMB and ST, is largest for 8.5, the red lines, intermediate for 4.5, the green lines, and smallest for the G4, which is again 4.5 plus an assumed SAI scenario. For the surface mass balance, the response is of course negative because climate warming generates more melting, and more melting means a more negative surface mass balance of the ice sheets. While for surface temperature, it's opposite. Warming directly means larger surface temperatures. We used 2 ice sheet models for our study, namely Psychopolis and Elmer ice. They're quite different. Psychopolis is based on finite differences. It uses shallow ice shelf stream hybrid dynamics, an enthalpy method for ice thermodynamics, and it has a regular structured grid with 5 kilometers constant resolution. Elmer ice, by contrast, employs the finite element method. We use it in the so-called Elmer ice sheet setup that has shelfy stream dynamics and no thermodynamics. And because it's a finite element method, it has an unstructured mesh with like almost 200,000 nodes forming a bit less than 400,000 triangular elements. And this method has the advantage that we can resolve areas of larger interest better, such as fast-flowing ice streams and outlet glaciers, while the interior of the ice sheet, where not so much is happening, is resolved less. These two plots show the simulated mass loss of the Greenland ice sheet expressed in terms of sea level contribution. So it's just equivalent. Yeah, mass loss is converted to water distributed over the world's oceans, and this produces the equivalent sea level contribution. The time scale is until 2090, as mentioned before. And first of all, we have these black lines in both cases, and these are the results of a so-called control run in which no climate forcing is applied, but rather the climate is kept constant at recent conditions. And in this case, we see that the model drift of Psychopolis is very small. The ice sheet remains essentially constant, while Elmer ice shows a significant model drift towards a growing ice sheet, negative sea level contribution. And this is simply because Psychopolis has been tuned quite carefully for this, keeping the ice sheet constant at present-day climate conditions, whereas for Elmer ice, we just used an off-the-shelf setup. So it has not been as carefully tuned as Psychopolis for the purpose. The colored plots are, like before in these climate forcing plots, the results for the individual climate models. Whereas again, red is for the RCP 8.5, green is for the 4.5, and blue is for the G4, and same for Elmer ice. And what we see here is that we look at the results relative to control. So for instance, red minus black, or green minus black, or blue minus black. The results are actually quite similar for the two ice sheet models. These plots show basically the same thing, but only for the final year 2090 and now relative to control. Again, to the left is Psychopolis, to the right is Elmer ice, and the mass loss is shown as a sea level contribution. For this group of bars here, the left one is for RCP 8.5, the middle one for 4.5, and the right one for G4, same for Elmer ice. The 4 colored bars are the results for the 4 different climate models, while the gray bars are the ensemble mean of the climate models. So as I said before, we see that the results relative to control are actually quite similar for Psychopolis when compared to Elmer ice. And the most interesting comparison is for G4 relative to RCP 4.5 in both cases, because this really isolates the effect of the additional stratospheric aerosol insertion. Please remember that G4 is actually RCP 4.5 plus SAI. So this comparison shows us directly what the gain of the stratospheric aerosol insertion is. And it's in both cases for Psychopolis and for Elmer ice on average, with some uncertainty, of course, the mass loss is reduced by about 1/3 if we employ G4 compared to just RCP 4.5. So that this 1/3 is about the gain of SAI. What these plots also show is the breakdown of the mass loss in terms of surface mass balance contribution, which are the circles in the plots, in the bars, and carving contribution, which are the plus signs. So we see that in all cases, almost actually surface mass balance is dominant. Yeah, so the loss due to surface mass balance change is larger than the dynamic loss due to carving. However, the effect is a bit different for Psychopolis compared to Elmer ice, such that there is still a relatively, not absolutely, but a relatively larger carving contribution for Psychopolis. We see that the plus symbols are generally larger here, While if you look at Elma ice, we see that the plus symbols, the carbon contribution is smaller compared to Psychopolis, and the SMB contribution is much more dominant. This one shows in a bit more detail than before the simulated ice thickness and mass flux changes, again by the final year 2090. And these plots are for the ensemble of climate or Earth system models, and they show in all cases G4 relative to RCP 4.5. So again, isolating the effect of the stratospheric aerosol insertion. The left two plots are for Psychopolis, the right two plots are for Elma ice, and we see in both cases the difference in ice thickness and the difference in mass flux, which is defined as the depth integrated horizontal velocity. So if you look at the thickness, the results look very similar for Psychopolis and for Elma ice, and we see that in the interior ice sheet not so terribly much is happening. So blue colors actually mean a slight thinning for G4 relative to 4.5, but it's very small. Yeah, it's just the scale is non-linear, so it's just meter scale. But much more pronounced is the effect all around the ice margin, where we see these red and green colors dominating. And this tells us that the thinning of the ice sheet is clearly less in G4 compared to RCP 4.5, which is a good thing. So the protective power is strongest near the ice margin. That's not very surprising because this is where the most impact of climate change on the Greenland ice sheet happens anyway. So for the mass flux, we see blue colors dominating, which means a relatively lower flow velocity, which could be translated as a smaller acceleration of outlet glaciers and ice streams. Again, G4 compared to RCP 4.5, and that's of course also a good thing because it tells us that under G4, the mass loss due to accelerating outlet glaciers and ice streams is less pronounced than for RCP 4.5. But here we see the difference between the two ice sheet models, Psychopolis and Elma ice, what I mentioned before. Psychopolis has a relatively larger dynamic contribution, more pronounced difference between the scenarios, while in Elma ice it's less pronounced. Yeah, so we see here the blue colors are much lighter than in the Psychopolis results. So Elma ice does not respond so strongly in an ice dynamically, but it has more of the effect due to surface mass balance change. Okay, so a short summary of this particular study. So we have seen that the mass loss of the Greenland ice sheet, if we first compare only the two climate change scenarios, is a bit more than 1/3 smaller under RCP 4.5 compared to under RCP 8.5. And quite similarly, about 1/3 under G4, which is RCP 4.5 plus SAI compared to just RCP 4.5. We have also seen that the partitioning between the surface mass balance and carving is quite different between the two ice sheet models, such that there is relatively more carving for Psychopolis and relatively more surface mass balance effect for Elma ice. All right. So it seems that SAI can do something good in protecting the Greenland ice sheet to some extent. However, I would really like to stress that this study is by no means meant to be a plea for SAI testing or even implementation. Geoengineering, as you certainly know, is generally speaking a highly contentious topic. So some of the arguments in favor, also underlined by the study I just showed you, are it may be a tool to mitigate some of the worst aspects of global warming, such as mass loss of the Earth's ice sheets. A bit more colloquially speaking, we could say we won't make it without it. Geoengineering may buy some time. It may compensate some remaining unavoidable greenhouse gas emissions, and it specifically when we think about the ice sheets, it might be a way to work against an already ongoing or committed instability of the West Antarctic ice sheet. I haven't mentioned this here, but this is a long-standing topic in the scientific literature, marine ice sheet instability, West Antarctica, and there are actually at least some indications that such an instability has already started for West Antarctica. And the discussion is, could it possibly be stopped or at least reduced by particular geoengineering techniques? Counter arguments are geoengineering may serve as an excuse to delay tackling the root cause of the problem, which is reducing greenhouse gas emissions even further. There may be adverse side effects. We are dealing with a very complex system, and these effects might hit people who have not demanded it. It's resource consuming. Resources are limited. We would have to invest a lot of work time, money, energy, logistics for whatever geoengineering techniques we might consider. My personal stance towards the problem is quite a skeptical one, I should say. Technology brought us to the edge of the climate disaster, and now the idea is geoengineering, even more technology, is supposed to fix it. There is a good quotation by Albert Einstein that says we cannot solve our problems with the same thinking we used when we created them. And I think this expresses my feeling about geoengineering pretty well. However, I should say that I'm not against doing further research into the matter, evidently. Otherwise, I wouldn't have shown you the results of this study. The ideas are out. So I think it's better to understand them openly in the scientific community and try to understand also possible implications, side effects, and so on, and not just leave that to the corporate world who would do it anyway. So let me just mention that next year there will be a conference, a joint assembly of 3 IUGG associations, the Atmosphere, Cryosphere, and Ocean ones. It's in mid-July, also in Busan, and there will be a session co-convened by myself about prospects and perils of geoengineering in the cryosphere and the oceans. So if you're interested in the topic, please consider it. That being said, I'd like to thank you for your interest. And finally, I'll show you the references I used for preparing this talk. So thanks again and goodbye.